So here we're looking at whether the integral would converge or diverge, or convergent or divergent, just depending on the part of speech. So what we have here, when we go in and we compute our Laplace transform using this definition, notice what will happen. Take your function, it's defined for non-negative values of t, you plug it into your improper integral, you get back whatever expression you get back. But while you're computing that expression, you're going to have to take a limit, and when you take that limit, if the limit exists, that'll be where your answer, where your Laplace transform exists. In other words, it converges. And you may also have places where your Laplace transform then diverges or is divergent, and this is where that limit would not exist. And just to remind ourselves, there's 3 places where the limit doesn't exist, or 3 types of way the limit doesn't exist. The proper does not exist, where there's nothing you can tell about the limit whatsoever. And then don't forget, positive and negative infinity is also a type of does not exist. Special type of does not exist, but still a type of does not exist. So for us, we're going to look at where does this limit exist, specifically what S values you can use to make sure that our limit is going to converge and not diverge. That's actually how we find the domain for these Laplace transforms. Okay, so that's the theory in the background. So let's actually work an example and see how this would happen. So the very first example that I've got prepped up for us is we would like to compute the Laplace transform of 1. In other words, what would you do if you just had a constant? And I'm going to focus on 1, but the same exact strategy would work if you had a 5 or a 7 or a 3 or a negative 10. Okay? So first thing is I'm just going to go ahead and write out our definition. So put down the little symbols. So here we've got the Laplace transform of 1. Just applying the definition, this would be the integral 0 to infinity of e raised to the negative st, and then you multiply it by the function, so you multiply by 1. Note, no, you don't have to put multiply by 1 there, it's just a 1. If, however, you had some other constant involved, like, I don't know, I think I've done in previous semesters asked you guys to say, what's the Laplace transform of 5? Well, in that case, you'd actually have a number down here like a 5. And you could just pull it out front if you wanted to. So here, if we want to compute that integral, it is an indefinite integral. In other words, there's a horribleness, the technical term, not really. There's the part we can't actually deal with because it's not a number, it's a concept, that infinity. So we'll go ahead and rewrite this as a limit. So we've got the limit as n approaches infinity of now the new integral 0 to n. And we're going to compute e to the negative st. Okay. And that's it for setup. Okay. Next step is we'll go ahead and actually do some computation. So limit, this part is going to hang out until the very end, but we can go ahead and find our antiderivatives. So quick check. I'm just going to do this over to the side so we remember our integral rules. If you have some integral, e raised to something, maybe something like, I don't want to use an a, what's a nice number for a constant? How about c for constant? Anybody remember what the antiderivative is if you have e raised to some coefficient, some number, times t? Oh, yes, so I see the answer for this one here. I'll do it in 2 steps for everybody else. Now this one would be, technically there's u substitution involved, where your u would be the c times t. It'll turn out to be the reciprocal of whatever that coefficient is on the exponent multiplied by the original e part. Okay? So in our case, if we go ahead and plug in our e raised to the negative st, that st, not st, that negative s right there, that is your coefficient. So the antiderivative here will total be 1 over s, specifically negative 1 over s, e to the negative st. And technically speaking, there's a plus constant on the end, but I'm not going to worry about it right now because, any guesses why? Why would I not need to worry about that plus constant that we've been worrying about the entire semester because it was important previously? Yeah, it's not going to affect the limit whatsoever. In fact, it's not going to affect the integral whatsoever because this is a definite integral. You actually have upper and lower bounds. And if you recall, you should have been shown this back in a Calc 2 class. If you put in the plus c, they actually cancel. There'd be a plus c in the first part, and then you subtract, and there'd be a plus c in that second part too. So next step, we'll go ahead and we'll plug in. So we've got the limit as n approaches infinity. We plug in the n into our formula. We'll have negative 1 over s, e to the negative s times capital N. Then subtract, and now we'll plug in 0. And when we plug in 0, we'll get negative 1 over s. And what happens to this e part when we plug in 0? And remember, you're plugging in 0 for t. Yep, it'll just be e to the 0 or 1. Or in terms of what I'm writing in that last line, I can just close off that second term once we have that negative 1 over s. Okay. Now, at this point in time, we're ready to go ahead and take our limit as n approaches infinity. Will the limit affect that second term, that term that was subtract negative 1 over s? Yep, not a chance. So what we've got here is, and I'm going to flip-flop it on you, 1 over s, there's the second term out front, minus the limit as n approaches infinity of 1 over s e to the negative s raised to the n. Okay? So what we have to figure out is we just have to figure out that second term. Now, any guesses what this thing is going to equal? Ooh, I have got such disparate guesses. I love it. All right, so let's look at it a little bit more carefully, shall we? All right, so let's look at over to the side. We'll go ahead and we'll look at our limit. So if we look at the limit, and notice here our limit, the only thing that's going to change in the limit is the e part. So I'm just going to focus on this e raised to the negative sn. Okay? Once we figure out what that limit equals, we'll multiply it by 1 over s, and then whatever that was, we'll subtract it from 1 over s. Okay? So notice what happens. We've got the n. The n is going to infinity, so that's getting really, really big. And then we have this s. S is just a constant at this point. It's fixed. Technically speaking, it'll be your new variable, but as of right now, it's what's known as a parameter. In other words, you're not assuming that it's moving. It's not acting like a variable. It's literally frozen in place. It's like when we did partial derivatives, and we did the partial derivative with respect to x. If there was a y in the formula, the y was acted like a constant. In other words, it was fixed. Same deal is happening here with the s. So you can think of it like a constant. I'm going to claim that there are several options. Okay? Well, what happens if s is positive? Well, if s is positive, you'll have some positive number multiplied by a negative out front, or a negative. So this whole thing will be negative. And then n is getting really big towards infinity, but if somebody's getting really, really big towards infinity, it's multiplied by a negative number, what's going to happen to that exponent? Well, the whole exponent would approach, and I guess is what that exponent would approach when you're dealing with s is positive. So only got two options. It's either going to approach infinity or negative infinity. When s is positive, Oh, I love it. I have both guesses, both positive and negative infinity. One of them is correct. Anybody else have a guess? Oh my. And the guesses stay split. It turns out if S is positive, S times somebody going to positive infinity will still be positive infinity, and then you have the negative up top. So this thing is actually going to go to negative infinity when S is bigger than 0. So that guy will go to negative infinity. Now, what happens to an exponential or an e when the exponent goes to negative infinity? Anybody have a guess of what happens with this limit when the top is going towards negative infinity? In other words, we're looking at this situation. Yep, it is totally going to approach 0. So I'm going to get rid of the scratch work because this is so improper math-wise whatsoever. We'll pretend we didn't write it. And that guy is going to go to 0. We're just going to do the same thing in the other cases. So the other case that we have is S is less than 0. So if S is less than 0, negative S times n is going to get closer and closer to who? If S is less than 0. In other words, it's a negative number. This time we're going to go to infinity. Why? Because the negative out front, negative S, is going to flip the sign, so that would be positive. Positive times somebody going to infinity would still be going to infinity. So this means the entire limit would look something like this. It would look like an e raised to an infinity. And what's that approaching? Yep, so that one is actually approaching infinity proper. Now there's one last case. Anybody have a guess what the last case is? Yep, so the last case is when S equals 0. So I'm going to go ahead and get rid of our scratch work there to the side. Oh no, the infinity disappeared. Just a second, we'll put the infinity back in. So when S equals 0, what happens? Well, you get 0 up here. 0 times somebody approaching 0 is, well, 0. And so e raised to 0 is 1. So you actually have 3 different cases here. So turns out, though, we're not going to need this last case. Here's why. You notice you have the 1 over S. Can you actually have S equaling 0? Is it possible in this scenario for S to equal 0 and still get an answer? Nope, you'd have a 1 over 0. So this guy, we're going to exclude this case right here. Now, when we come over to finding our final answer, we want a formula that actually exists. Can we plug in to get a formula that actually exists if S is smaller than 0? In other words, is it okay to have this case when S is smaller than 0? Again, no, because we're going to get an infinity and we want an actual answer. So we're also going to cross this guy off, not because we didn't like the less than 0, but because we didn't like the infinity. So that means we're only going to plug in the case where this limit equals 0. So that means we're going to have 1 over S minus 1 over S times 0. And now we have the new stipulation that S must be bigger than 0 for us to actually get that answer. Now, let's finish it off. What does that mean we really had? Yep, so we really had here just that first term, that 1 over S, and we also got our domain of our Laplace transform. So what this tells us is if you are needing to find the Laplace transform of 1, it is exactly the same thing as 1 over S, and the domain of that Laplace transform is positive values only for S. That's it. That's your first rule for Laplace transforms. Unless your question in the future says use the definition of the Laplace transform to compute it, and if it says that, this is the work you'd have to do. If it doesn't say use the definition, it's totally okay just to pull the rule right here. So what we're going to get as we're building these Laplace transforms, we're totally going to get rules just like derivative rules, just like integral rules. It's just going to be a list of rules. And I don't know if you guys saw it yet or not, but posted on the Canvas, I already posted the rules for Laplace transforms for the continuous functions. It doesn't have the non-continuous functions on there, but we'll get them based on the current time, probably on Tuesday, we'll get to the discontinuous functions. But that's it for the first Laplace transform. Everybody okay so far? Questions? Made sense what we did? Seeing no questions, I'm going to assume that you guys are okay for now. And if you find it's not true, just shout out the question. Or I guess type out since you're all muted right now. What I would recommend is as we're going through this, write down the rule. So if you write nothing else down, I would recommend writing down that the rule for the Laplace transform of 1 is 1 over s. Because we're going to need it in the future. That future might actually be the very beginning of next class period, but we will need this in the future. All right, so next example. So the next example that I got for us is us building our second Laplace transform rule. And here's the Laplace transform we're going to care about. So Laplace transform of the function e raised to the at. So this is the function, it's the part between the curly braces, the e raised to the at. We are going ahead and assuming that we're only looking at when t is equal to 0 or bigger. That equals part on the greater than or equal to is really tight to the bottom title there. Sorry about that. And the a in the exponent is just some constant. So in practice, how would you use this guy? You might say, hey, I need the Laplace transform of e raised to the 2t. That's how you'd actually see it in practice. All right. So this one here, there are some key things to notice. It does say use the definition to compute this. So for us right now, we're going to go ahead and build to the rule. If your example in the future or your question in the future says compute the Laplace transform, and it doesn't have this initial clause right there, you can just use the rule we're going to get at the end of this example. All right, so we're going to do the exact same thing as the last example. So Laplace transform, e to the at. Going to go ahead and just use our definition. So this was 0 to infinity. We have e raised to the negative st times now our function e raised to the at. Now I went ahead and picked the two examples that we've done here. The previous one with a 1 because 1's awesome, and this one because the e to the at is going to combine super nicely with the part that you always multiply your function by, this e raised to the negative st. We've only got one more example that I'm going to look at in terms of building up to functions. Everything else is, I'm just going to give you the rule, and we'll go through it from there. So next thing to do, well, there's two next things to do. One of the next things to do is we want to go ahead and convert our improper integral into the limit of, and then we'll use the capital N like before. But before we do that, let's go ahead and combine these e's together. So if we combine these e's together, what happens? They both have the same base, so you're just going to add the exponents, and I'm going to be a little sneaky, and here's my sneakiness. I'm going to say this is the same as negative times s minus a all times t. Right. So if you just straight up added it, I'll show you the work over here to the side. So we have e raised to the negative st plus at. That's exactly the same as you could totally have just said a minus s times t. Now, is this the same as what I wrote out? What do you guys think? Is it really the same thing, even though they're written differently? Yep. The only thing I did is I factored out a negative. So I factored the negative out of s, so it went positive. And I factored a negative out of a, so that flipped its sign to negative. And I totally did that on purpose, but there's no reason you have to do it that way. As long as you combine your e's together so that you've got some constant, your a minus s or your negative s minus a here, multiplied by t, you're going to be fine. And remember our rule that we had previously, we said the integral of e raised to c times t was exactly the same thing as the reciprocal of that constant times e to the ct. Because I use c's, I definitely did not put in the plus c for the plus constant at the end. So let's go ahead and put in the limit. So we'll have the limit as n approaches infinity. Replace the bad infinity. Okay, infinity isn't really bad, it's just unwieldy right now. With an n up there in the upper bound, and then we still have our same function. And please note, as you're working this, it's totally fine to combine steps. I just went ahead and put all the separate steps here because it's the second time that we've dealt with the definition of the Laplace transform. Which means we'll go ahead and compute the antiderivative. So here your antiderivative would be, what would that be? Negative 1 over s minus a, e raised to the negative s minus a. Do a quick check, make sure I actually did that derivative rule correctly. All right, so now we need to plug in and then take a limit. So when we plug in here, when we plug in capital N, pretend that was an infinity, plug in capital N, we'll have negative 1 over s minus a, e raised to the negative s minus a times capital N minus, well, we're going to have another minus, so it's really going to turn into plus. And when t equals 0, this whole exponent will be 0, and the e term will turn into 1. So you really just have the 1 over s minus a at the end. Now, you should all be thinking to yourself, wow, this looks super duper similar to the example we literally just covered. Anybody spot what the only difference is between this example and the thing we just did at this stage in the work? You got it. Literally the only difference is we now have s minus a everywhere there was an s previously, and that right there is the reason why I went ahead and wrote the exponent on the e here funky, mainly so you could see that's change out. And that's one of the reasons why I said totally fine if you use the other way, if you're doing it all by yourself. But doing it this way, I wanted to go ahead and point out at this moment, hey, we swapped out the s for the s minus a. Now, notice what that tells you. That's actually going to tell us something about our e, specifically when we're dealing with the limit. So if we look at the limit, wow, that m did not work out well. As n approaches infinity, of e raised to the negative s minus a n, it is going to equal potentially 3 things. It's actually going to equal the same 3 things we had before: 0, infinity, or 1. Now previously we got 0 when s was bigger than 0, infinity when s was less than 0, and 1 when s equaled 0. Except now we've replaced the s that was our coefficient on the n with s minus a, so that also changes in the piecewise function. You replace the s with an s minus a. What does that really mean? That means this is the stupidest way to write that ever. How should we have really written those conditions? For example, the first one, which is the one we care about. What's a better way of, So the better way of writing this is totally s is bigger than a. Now, let's apply that to our limit. So this tells us that we have the limit as n approaches infinity, first term equaling 0, plus 1 over s minus a, and this occurs when s is bigger than a. Notice, just like before, we're going to have some issues, and specifically, where did the cursor go? We're going to have issues at this last one, and I already scratched it off. That is regrettable. That last thing would be when s equals a. Notice we can't use that one still because you get a divide by 0 right there. So we'll go ahead and clean this up. And what should that limit actually equal now? Anybody got a guess of what that limit, or specifically what the Laplace transform of e to the at is going to end up equaling? Ooh, it's not 1 over s, but you're close. Yep, it'd be 1 over s minus a. Now, let's do a quick application of how you would actually see this. I hate to say in the wild, but let's go with it, in the wild. So suppose you have the following example. Suppose you were asked to compute the Laplace transform of E raised to that, well, we said 2t before, so let's be lazy and say it again. Any guesses what the Laplace transform of that guy would be? And notice I didn't ask you to use the definition. Laplace transform of E to the 2t. The assumptions here is that t is good for 0 and above, or 0 and bigger. Yep, that's literally all you do. So in this case, a equals 2. Just apply the rule. You'll get 1 over s minus 2. And in terms of the domain, your domain would be s is bigger than 2. And that's literally it. So what I would definitely recommend is once we get all these rules, write them up on your own piece of paper. Keep that piece of paper next to you as you're starting to go through this stuff. Eventually, you'll need to memorize this stuff, but for our course, I mean, if you have it for the rest of the semester, that's okay. But eventually, when you start using this a lot, you're going to get these guys memorized. And notice that's as quick as doing like a derivative rule or a basic integral rule in the same vein. Questions make sense? Kind of feeling okay-ish. Ish being the key word there. Can at least follow it when I do it. I got a couple responses to that one. Okay. All right, so let's move on to the next thing. So the next thing is actually some properties, and we're going to use these properties. So the first thing is something called linearity. I do not care if you remember the word linearity, but here's where it means. It means you can take whatever function you have, you can multiply it by a constant, a coefficient, and be totally cool. It means if you have two functions and you add them together, you can totally just take the Laplace transforms of the individual functions and be totally fine. Notice this is the exact same thing you could have done with With your integrals. Why? By definition, this first part here is the same as the Laplace I didn't want Laplace transform. Just a second. It's exactly the same as the integral, 0 to infinity, of a times f plus b times g. I was lazy and didn't put the t's, times e to the negative st. It's an integral. Distribute everything out, so you have af e to the negative st. You've got bg e to the negative st. And what do we know about integrals? You can totally break this stuff up. Pull the constant a and b out front. You can't pull the f and the g's out front because they potentially have t's involved. And notice this is how you get your Laplace transform of f and your Laplace transform of b. This works 100% because they're built from integrals. Now, how would this actually work? So, example. Suppose you have something like this. Suppose you have 5 plus 2e to the 3t. I'm going to claim, and see if you guys believe this. I'm going to claim this is exactly the same as 5 times the Laplace transform of 1 plus 2 times the Laplace transform of e to the 3t. What do you guys think? Was that a correct application of this property? Looks fairly believable. Looks like a couple of you are agreeing. So what's the advantage of this property? What can we do now to go ahead and solve for the answer without using the definition, just using the two rules that we have so far? What would that first term turn into, in other words? So the first term would turn into, well, Laplace transform of 1 was 1 over s. So 5 times 1 over s is 5 over s. I always forget my 5's and s's look similar, so that's problematic. And then we look at the second one and notice what happens there. So this part was the same as 1 over s. What was the Laplace transform of e to the 3t? Yeah. Yep, I've got a couple of you sending that in. So this one here would be 1 over s minus 3. So putting this together, multiply the 3 by the 1 over s minus 3, and this would be 2 over s minus 3. Notice that's the same thing you guys do sort of automatically when you're dealing with integrals or actually derivatives. Same thing applies here with Laplace transforms. Questions? Make sense? Kind of okay so far with that property. That property is a big deal because it's how you link the various rules together. In the formula, and let me see if I can go back. Okay, just a second. In this formula right here, the A part of that formula will always be the coefficient on your t. So it's always going to be some constant times t. Does that answer the question? But it'll always be some constant. It can be negative, it can be positive, but it'll always just be the coefficient on t. All right, so that's it for this one. There's one more property, and then we'll get into another rule. All right, so the second property is called a translation property. Again, I do not care if you guys have the names of these memorized or not, but the translation property goes as follows. It says, hey, you get some function, whatever function you want, we'll call it f, and it gets multiplied by e raised to a times t, where the a is that same a we had before, but some coefficient, some constant times the variable t. It turns out if you do this, this is exactly the same thing as the Laplace transform of the function f, but replace all of the s's with s minus a. Okay. So what this would be like is it would be like saying the Laplace transform of f, but you replaced all of your s's, swap them out with s minus a. That's what that actually reads as. Okay. Notice what also is going to happen when you shift it or you do a change of variables. You're literally, this is the same thing in algebra where you move your function right, this is t's, so this would be moving it right or left, depending on what a is. So that also means that your domain for your s is also going to shift, and it's going to shift from the standard s is bigger than 0 to s is bigger than whatever your a was, and that a comes from that constant, that coefficient up there in the exponent of e. Okay? Kind of makes sense, slightly makes sense. I'm going to assume slightly, and let's see how this would work in an example. So next thing is an example. So suppose we go back to the question that we just looked at. So we looked at here, Laplace transform of e to the at, and we already solved it simply using the definition of the Laplace transform. Now I want to go ahead and use rules. So here is a rule that we know. And I'm going to skip out on the rule we built because we're trying to do it again. Not just going to sort of phone it in and say, hey, what the answer is. So we said previously that the Laplace transform of 1 was 1 over s when s is bigger than 1. And the property that we just had said that if you multiply e to the at times any function, what you'll get is the Laplace transform of that other function, but switch out all of your s's for s minus a. And you'll also get a new domain of s minus a. So that's the properties we're going to use. So grabbing Laplace transform of e to the at, the thing that we care about, that guy, it is multiplied by some function. Anybody got what function it's actually multiplied by? In other words, what is our f of t? Yep, so this guy would just be a 1. This is a sneaky answer. Okay. So this means we want to compute the Laplace transform of 1 and then switch out whatever s's we get with s minus a. Okay. So what did we say the Laplace transform of 1 was? Hopefully you were all thinking 1 over s from right up here, right where that hand is. So I'm going to write down 1 over s. Now, we still have to switch out the s with s minus a. So when we do that, we're going to get 1 over s minus a, and then the new domain is s is bigger than a. Now, is that the same answer we got before? I got a couple of you guys saying yes, yep, it is still that same answer before. For this one, you can actually find it in 2 different ways. One of the ways is just a straight up rule we built from the definition. The other one is use this property to apply to the rule we had before. Either way, totally fine. I can't do any examples other than this for this rule right now just because we don't have any other examples. But in this case, you get the exact same rule as before. And that's it for that property. All right, so the next example I've got prepped up for us deals with building the Laplace transforms of sine and cosine. Your book, I don't know why he does this, but your book goes and actually uses the definition of the Laplace transform again. We're not going to do that. That's the last time we've used the definition of the Laplace transform today. Everything else today and pretty much in the future is going to be just us using rules and properties. I'm going to show you a trick on how you can build the Laplace transform of cosine and sine. Okay. So here's the first thing, is we need to remember a fact. And we've used this fact once before. I am not assuming that you've remembered this fact, but once I wrote it down, hopefully it was vaguely familiar. So this is the rule. And I'm going to write it the same way that we wrote it before. It says e raised to the imaginary number I times theta, where theta is any angle, is exactly cosine of whatever that angle theta is, plus I times sine of that same angle theta. Now for us, we want to compute the Laplace transform of cosine of kt and sine of kt. So for us, we're actually going to plug in theta equals kt is what we're going to do. So I'm just going to go ahead and write that out for us. So e raised to the I times kt. That'll give us cosine of kt plus I times sine of kt. Wow, that was terrible k. Let's try to fix that just a little bit. So it's actually readable. Yeah? So that's the background that we need. Now, next we're going to use our linearity property. So linearity property says what? It says, hey, I can actually take the Laplace transform of both sides. And if I take the Laplace transform of the left-hand side, it'll simply be, hey, the Laplace transform of e to the I times kt up in the exponent. And on the other side, if we apply the linearity property, we're going to get the Laplace transform of cosine plus I times sine. Linearity splits that. So this last part right here, we can split it up as simply the Laplace transform of cosine. That's trying to be a t, I promise. Plus I times the Laplace transform of sine. Now, notice what this tells you. This tells you that if we can compute the Laplace transform of e raised to the I times k times t, the imaginary part of that answer is going to turn into, or is going to be exactly the same as the Laplace transform of sine. And the real part of that answer is going to turn out to be the Laplace transform of cosine. Okay? That's a trick. Okay? Now, we'll come back to this at the very end, but next let's go ahead and just compute the Laplace transform of e to the I times kt. Now we'll use our rule. Okay? So use rule. And the rule that we've had was Laplace transform of e to the at was the same as 1 over s minus a, and your s had to be bigger than a. So here's the big question. What in the world is our a in this case? Anybody have a guess? You got it. So the a in this case is going to be that I times that k, those constants that are being multiplied by t. Notice here it is totally okay for the a to be a complex number, a number that includes the imaginary number I. That's actually one of the really, really nice things about Laplace transforms is we don't have to just stick to real numbers. It's okay to jump into using imaginary numbers too. So if we go ahead and I'll put it over here to the side, a equals I times k. We'll apply our formula, and our formula says we have S minus I times k. Bam, the answer is beautiful, it's perfect. And then you try to compare this thing to the real part and the imaginary part, and you're like, yeah, no, that looks horrible. The answer is, you're right, it is. So what we need to do is we actually need to move that imaginary number I up to the top of the fraction. Anybody have a guess how we could move the I component up to the top of the fraction? Hint, you got to multiply by something. Unfortunately, you can't just straight up divide by I, but it's sort of the adjustment. Oh, I love your guys' guesses. Okay. I is what, to remind ourselves? So our scratch work over here to the side, where I totally should have done the rule as well. I is the same as, you're all thinking, hopefully in your head, square root of -1, which means this is a square root. Huh? What do you do if you want to move a square root from the bottom to the top? There we go. We're going to rationalize the denominator here. Now, if you don't remember what the word rationalize the denominator, or I guess the phrase rationalize the denominator means, don't worry about it. Okay? What it means is we're going to take the same thing we had on the bottom and multiply by that same denominator, except flip the signs. So if they were originally added, you'll subtract. If in our case they're originally subtracted, we'll make everything added together. Then make sure you have the same thing on top. When we multiply through, we'll have S plus I times k. And in the denominator, we'll get S squared minus I squared k squared. Now, what's awesome about I squared? Yep, it equals -1, so that denominator is exactly the same as S squared plus k squared. Why? Because if you do subtract the -1, that's totally going to turn into +1. Okay, so there's our scratch work with the imaginary numbers. Now, this is actually extraordinarily awesome for us because you can rewrite it as S over S squared plus k squared plus I times k over S squared plus k squared. Now, I'm going to claim at this point, this tells us exactly what the Laplace transforms are for sine and cosine. They are both going to be over S squared plus k squared. Now, if we distinguish between the two of them, anybody got what the top of cosine should be? So the top of cosine would be S, and that's because this term here had what? It has no imaginary parts, and we said cosine up here was supposed to be the term that had no imaginary parts. So what does that mean about sine? What should be on the top of the fraction for the sine? It'll be just the k, because notice here, your sine is being multiplied by your imaginary number, so this right here would be your Laplace transform of sine. And that is a way to get around dealing with the definition of the Laplace transform And if you want to see how crazy it can be of using the Laplace transform, definition of the Laplace transform to go ahead and compute these two guys, look in your textbook. He goes wild with it. Okay? But we got a couple minutes left. Let's play around with a couple of examples with Laplace transform of sine and cosine with actual numbers and see what some of the things are that you can do. Okay? And we actually already did this. I thought it was going to take longer than it did. So we're not going to do that. So let me write the rules over here to the side. We had the Laplace transform of 1 was 1 over s. We had the Laplace transform of e to the at was 1 over s minus 1. We've had the Laplace transform of cosine kt was s over s squared plus k squared. And the Laplace transform of sine of kt is k over s squared plus k squared. And next time we'll get polynomial guys, which is that and discontinuous functions are the only ones we have left. We also had some properties. And the properties that we had were linearity. So this says if you have coefficients, just break it up, totally fine. Pull the a out, and then just look at the Laplace transform of f. And for that second term, pull out the b, and just look at the Laplace transform of g. And we also had what happens if you multiply e to the at by any function. And this turns out just to be the Laplace transform of that other any function, but switch out the s with an s minus a. And I didn't write down the domains. Now, any guesses what this guy would be? Any guesses what we would do to find those two rules? And there's utter silence. Ooh, yes. So key thing to go ahead and find those two rules is we're going to use this last rule right here, which says we're going to use the rule for sine and cosine and just replace the s with an s minus a. That's literally it. So this top one up here, we'll take the rule for cosine. We look over here at cosine. That is an s on the top, so we'll write s minus a instead. We have s squared, so we write s minus a squared, and plus k squared. Sine's even easier. There's only a k on top, so no change. And on the bottom, s minus a squared plus k squared. Notice those are two rules that I would definitely recommend putting on your list to know, but you technically don't need them because you could use this shifting rule or translation rule at the bottom there. Okay. Let's look at a couple of examples here with actual numbers. So if we look at this first guy, any guesses what that Laplace transform is? Well, the 7 is going to turn into what? We did one like this a little bit ago. Anybody have a guess for what 7 is going to turn into? Or what the Laplace transform of 7 is? Right, I've got a couple guesses coming in. Yep, you guys are all right. It's going to turn into 7 over s. And this isn't somebody that anybody writes down, but I have found it is super duper helpful to say, hey, the Laplace transform of any constant is that constant over s. I find that super helpful just to have that tucked away. Now, for sine, notice we have a 2. But here the main thing you want to do for sine and cosine is you want to identify what your k is. Who is your k in this example? Yep, your k is 3. So you get exactly what a couple of you guys have, almost exactly what a couple of you guys have typed in already. So our k here equals 3. The bottom of either a sine or a cosine, I'm over here at the side, is going to be an s squared plus k squared. So that's s squared plus 9. And since it's sine, you're going to have the k up top. So our k was 3. So if you wanted to go ahead and clean this guy up, this would be the same as 7 over s minus 6 over s squared plus 9. Okay. And that's it. The only one that gets slightly more interesting, and I'll end on this example, just so we don't forget what we were doing. Suppose you have this guy. Here, key things. Your k is still 3. Your a, your coefficient on the t, is 2. We're going to apply the formula right up there at the top. So we'll have s minus 2, s minus 2 squared, plus 3 squared, or plus 9. That's it. That's how you use these guys. Okay? So that's it for this time. Sorry about going over. So the plan for next time is we will go ahead and we will look at the last couple of rules and properties that we didn't get to today, and that will actually take care of all of the basics that you need for the Laplace transforms.